Okay, so the presentation is open for discussion, and there are 3 questions in the chat line. Sarah, would you like to read them out loud and answer?
Okay, let me find it.
Okay, then I can read them. So,
thank you.
And you keep sharing. So, from Professor Svetlana Hilina, why this amino acid is used? What is its name?
The name of amino acid is tyrosine, and I think we have 5 or 6 type of group for the amino acids. So we were supposed to select or choose one type of amino acid from each group for more calculation. So there wasn't any special reason why I choose tyrosine. I just wanted to just see the interaction between this tyrosine and the Montmorillonite. I think we can say that it's randomly we choose this type of amino acid. And for the future calculation, we are going to choose more type of amino acids and then explore its interaction with the Montmorillonite.
There is question number 2 from Professor Hilina. Do you expect an interaction between the molecule and its replica due to the small size of your calculation cell?
I didn't get the question. You mean the size? Yeah, go ahead.
Is there an interaction between molecule and its replica in the through periodic boundary conditions? Will molecule interact to itself?
Yes, of course, because it in the 3 sides we have the periodic cells. Yeah, doesn't have any vacuum in the X, Y, or Z directions.
Okay, and there is a third question from Professor Hilina. What is the oxidation state of iron in your system? Is it known from experiment?
I haven't checked the oxidation state for the iron. It's a good question. I appreciate it. I can double check it.
But what you were sorry, you were talking about the spin up, spin down case.
Yeah.
It means your number of electrons has to be at least even or odd. So any comments on that? Iron 2, it has 6d electrons.
Yeah.
How can you get spin up, spin down with 6 electrons?
It's a very good question. Unfortunately, I don't have background in this field.
Can you go back to the slide where you show the high spin configuration and low spin configuration? And from here, you may be able to figure it out. I think you go back a little. Go to slide number 7.
So your A panel, what do you show in the x-axis?
For this one?
Yeah, what is your x-axis?
This is the number of unpaired electrons. So the global minimum is when the number of unpaired electrons are equal to 1.
And I think 5.
Yes, 5 and 1 kind of have the same total energy, but for the n of down equal to 1, it's smaller a little bit in comparison with the 5.
But again, it looks like how many electrons you're putting on your on the panel B then.
Right. Yeah.
How many electrons do you have there?
5 electrons.
So if iron 2 is 6 electrons in a D level, then what iron you have in here, since it having only 5 D electrons?
When you remove
Iron
one electron, how does oxidation state changes? Is it increases or decreases?
So iron 2 plus has 6 electrons. Then you take 1 electron out. What you get? What would be the charge?
And I think now the oxidation state will increase.
For how much?
How much? Maybe we should say that.
So how much you change your oxidation state?
Maybe we should say that difference between the n up down equal to 6 to 5 minus n up down equal to 5. Yes, the difference between in this two number for the total energy, it should be.
No. Oxidation state. Like this concept means is it neutral or some electrons are removed? If oxidation state 2 plus means 2 electrons are removed. If you remove one more electron, what will be the oxidation state?
1? It should be 1?
No, if you add electron, it will be 1. And if you remove?
Okay, Sarah, there are 8 electrons. There are 8 electrons. I think for iron there is 2 electrons on a 4s, and there are 6 electrons on the D shell. So when you charge it with 2 plus, right, to get iron 2 plus, you're removing 2 electrons.
Yeah.
So first 2 electrons, they are gone from s orbital, and that's why you have only 6 on a D orbital. But then if you want to do iron 3 plus, you need to take 1 additional electron. And you can take it only from the D, because from S, everything is already gone to get 2 plus, right? So then removing 1 electron from D, it was 6 on a D, now it's 5 on a D, you remove 1, right? So you're getting now iron 3 plus instead of iron 2 plus. If you take even more electrons, 2 electrons off, it would be iron 4 plus. Yeah, you're removing electrons, your charge increasing, becoming more and more positive.
Yeah.
So just oxidation state, positive charge on the iron, right, showing how many electrons you took out from the neutral atom.
Yeah. Yeah, okay. Thank you.
More questions to Sarah?
Yeah?
Yes, please.
Yeah, sure.
Sorry, I don't want to dominate the forum, but if anyone want, have any question, please, get me out of the room. Okay, I'm glad that you dare to look at, the spin state of transition metal, because transition metal, are a different animal compared to other elements. So it's good that we had this discussion. Now in the calculation, you can control the high spin configuration or low spin configuration by using that flat, N up down, or sometimes you don't have to do it. You can do, other way to do it. But setting the value of N up down in the in-car file is usually not enough. We still have to look at the out-car file to see if we really have the high spin configuration or not, or low spin configuration or not, by looking at the calculated local magnetic moments, right? So let's say that let's focus on the high spin configuration and low spin configuration, right? For the low spin configuration, you had that, N up down equal to 1, right? So if you look at the out-car file, what is the value of the local magnetic moment at the iron side? Do you remember that value, or have you looked at that value?
No.
It's important to check it,
Yeah.
because you just impose some constraint on the calculation. It doesn't mean that what you get out is exactly what you want to have. So it's very, very important to look at it, because even if the total magnetic moment is what you expected, the local magnetic moment can be different. Okay. So in the case of low spin configuration here, I would expect that the local magnetic moment would be somewhere, closer to 1. In the case of high spin configuration, I would expect that the value would be 4 point something. Normally it would be lower than the maximum value, Okay. So it's a good exercise to look at the outcome file and double check it.
Okay. Yeah. Okay, I will double check it. Thank you.
More questions to Sarah? I have one, question or comment. So based on the figure that you are displaying, panel B and C, which one will provide lower minimal transition energy? Configuration B or configuration C?
I think B.
Why?
It's supposed to show that the lowest spin for the crystal field diagram, and
like show which electron with which spin is transferred by optical excitation.
Yeah, it should be this one. This
and where does it go?
Oh, it should go to the this level. Okay. Or an energy gap.
Okay. And is this transition available in the high spin configuration?
High spin configuration.
In the panel C, is the transition from T to G to EG is the same transition available or not?
No, I think.
So because of the spin conservation.
Yes,
right?
All of them are upward.
Okay, so you are telling that B should have the lower transition energy than C. Now let's go to your spectra and check if this hypothesis is correct or wrong. So which corresponds to B, which corresponds to C, and where is the transition energy is lower?
For the N up down equal to 1, I think this should be the range for the N up down equal to 1, the absorption. And for the N up down equal to 5, this picture represents that values. Am I right?
Yes. So does it agree with your hypothesis that N up down 1 has lower transition energy or longer wavelength?
Yes.
Okay.
Wavelength is around 2,050, 500, and this one is around 1,500.
Very good.
Nanometer. Yeah.
Okay. More questions to Sarah. One. More questions too. Oh, Professor Kilina, please.
Not so much to Sarah. It's more maybe to you because you probably were helping to choose. It looks like you were using iron 3 for this system. And then did you check that your total charge neutral? It's still neutral system.
It is neutral. It is a neutral system because water serves as the pool of charges. It can add or withdraw electrons from water. Total charge is 0. It's neutral system.
I didn't get. Where do you have water? You don't have water in your calculations.
Of course, we have for the whole system. Here are the water molecules.
Okay, I got it. So you have.
Yeah, water, Montmorillonite, and amino acid.
But then, why your water is not really interacting with your molecule? Why it's not really surrounding the molecule?
And this is just snapshots from after geometry optimization. But for the molecular dynamic, you can see that there are some interaction between the amino acid and water molecule, and also the clay surface.
Right, but
so the projects were done within 3 weeks. So one cannot judge for.
Water molecules, you probably need to increase your computational cell twice. So you will really have enough water to interact with both the surface and the molecule by itself. Okay, I got it. So you're just saying that you probably have, but it does, even if you have a water molecule, right? So it looks like you charging your surface, and then you expect that this charge will be kind of getting to the surrounding. Okay.
Yeah. Thank you.
Please join me in thanking Sarah.